it's fresh fruit on the kitchen counter or a Rembrandt masterpiece. Nothing lasts forever. Material is made out of stuff. Stuff is subject to forces and chemical interactions, and sooner or later, stuff starts to break down. This week's story might not be able to do anything about the fresh fruit, but this technology, studied in the journal Nature, might be able to help out that Rembrandt. Collections in museums have pieces centuries, even millennia old. Even in the best conditions, paintings accrue damage, and plenty of paintings have not been in optimal light and humidity conditions their whole lifetime. Art restoration is likewise, then, a centuries-old discipline, and it's a challenging one on many levels. First, there's sort of your philosophy of restoration. What kind of damage or alterations require intervention? Like big chunks of paint missing, UV damage, scuffs? Apparently, on a meter-tall painting, the human eye can detect scratches and imperfections, especially on a painted face, as small as 100 micron. A tenth of a millimeter. Now, once you've identified the things you want to fix, how will you do it? Are you going to engage in non-destructive or less destructive techniques like cleaning only? Or if a big chunk of paint is gone, are you going to infill? That is, paint in the missing pieces. That is a technically demanding element of art restoration. The person doing the restoration is trying to match painting techniques with the artist and make their retouching seamless with the original painting. Yes, there are notable examples of amateur restoration going horribly, horribly wrong. But real art restoration requires technical artistic skill, a strong foundation in art history, and excellent scientific understanding of the materials in play. When done right, the results are absolutely incredible. Indeed, the science and technology side of art restoration has really flourished. With high-resolution scans of paintings, restoration experts can use a range of deep learning approaches to do things like simulating cleaning, reconstructing facial features, and visualizing the results of a painting restoration. It's invaluable to have a visual reference of the result, and it helps experts strategize how they're going to approach a particular restoration. But as this week's study points out, what digital restoration tools don't do is get you from that lovely digital reconstruction to like a real-life physical one. To get from this sophisticated reconstruction to the material canvas and paints, the conservationist still has to do something. And a reconstruction of the final result isn't the same as a step-by-step to manually accomplishing that result. That's the problem they're trying to solve in this week's study. But when I say they, I specifically mean Alex Kachkine. See, usually scientific papers will have a handful of authors, especially papers in Nature, one of the most prestigious scientific journals. When I saw a solo author in not an editorial or a news piece, but a for-real scientific article in Nature, I did want to know more. So first of all, Alex Kachkine is a PhD student who recently passed their qualifying exams and is working on picking a dissertation topic. Why isn't their PhD supervisor or, like, anyone from their lab on this paper with them, then, you might ask? Because this project has nothing to do with Kachkine's PhD lab. Kachkine is part of the Velasquez group at the Research Laboratory of Electronics at MIT. It's a lab that studies microsystems that use high electric field phenomena. Like, normally, Kachkine's working on evaporation in mass spectrometry, which will make no appearance in this story. This project was entirely motivated by Kachkine's art collection hobby. They're a broke grad student, and damaged paintings are less expensive. So they applied their engineering skills to solve a problem in that hobby. So to summarize, this grad student's side hustle became a solo article in Nature. That is unbelievably badass. So, how does Kachkine try to bridge digital and physical art reconstruction? They print the infills in the digital reconstruction as a mask, then layer it on top of the original painting. You can see in the exploded layers, the painting remains intact, and the retouches are printed as a 2-layer laminate mask, which is isolated from the painting by conservation-grade varnish. It's such a galaxy-brain solution. And more importantly, it's a solution that fits with the American Institute for Conservation Code of Ethics and Guidelines for Practice as a fully reversible technique. Because at no point are you putting paint on the paint or anything. But how is it accomplished? First, of course, they scan the original painting and perform the digital reconstruction. From here, yes, they could make the mask literally every single pixel that's different between the original scan and the reconstruction, but that would be super aggressive and cover far too much of the original work. So, on what basis are we going to tone down this mask? Well, one is the difference between the pixels significant enough that humans could even perceive it? As far as digital color space is concerned, these are 2 different purples. So strictly speaking, every single pixel would be masked. But as a matter of art restoration, there's absolutely no way you'd ever infill a difference like that. Setting human perceptible thresholds, then, already gives us a more conservative infill mask. The other threshold limitations on our mask are our tolerances. How small a retouch can we actually print? Let's go back to this view of the laminate. You can see that there are 2 layers to the infill mask on that explosion there. The underlayer is actually a white layer, which is just the positive space the mask will eventually cover. Then there's the color layer of the film, which, in the case of the 15th century proof of concept reconstruction performed in this paper, includes 57,314 different colors. Kachkine went through a lot of trial and error to find the best printing techniques and materials to line those 2 layers up at the necessary levels of precision, so the white layer wasn't poking out from under or anything. And the final resulting technique allows for retouches as small as 0.5 millimeter in area, with individual touches just 42 micron within that area. And that might sound absolutely wild and like maybe an unnecessary level of detail, but artists like Jan van Eyck literally painted not with a brush, but a single hair. So, maybe actually not an unnecessary level of detail. These are scans of the final result after the proof of concept restoration was complete. The restoration is extensive and repairs a bunch of irrevocably damaged elements, but it also preserves the original work. There's obviously a difference between the retouched in-painted elements of the infant's head and the original paint that's cracked and discolored right next to it, down there on the bottom left, but all of that is in the name of preserving the underlying work of the artist who painted it. And if subsequent preservation experts want to take another attempt at restoring this painting, the digitally reconstructed mask has one more advantage: a perfect record of exactly what was done as part of this attempt. Think about it. In a manual reconstruction, even the best record-keeping doesn't track each paint stroke the conservationist makes when filling in a damaged section of a painting. When it comes to this physically reconstructed digital mask, you know exactly which areas of the painting are retouched and which aren't, and what was done. The other big advantage is time. Applying the infill mask took Kachkine about 3.5 hours, while they estimate a good old paint and brush would have taken approximately 232 hours to achieve the same. They estimate the overall restoration time would have taken months, which is apparently typical for restorations of paintings like these. Now, this technique isn't a panacea. For one, it only works with paintings that are materially or stylistically appropriate to use varnish with, so not frescoes, for instance. It's obviously also not going to work for paintings that use impasto techniques with a lot of 3D texture to them. It totally counters the aesthetic of the painting to throw a laminated film mask on top of something like this. And throughout the paper describing this technique, Kachkain's very attentive to the spirit and ethics of art conservation. Again, this is not their graduate field of study. I told you, there was no mass spectrometry here. But in digitally reconstructing the painting and developing a means to physically apply that digital reconstruction in a stable, reversible manner, Kachkain demonstrates respect for art history and conservation techniques. This isn't a AI disrupting the art conservation world technique, but rather a genuinely passionate art lover contributing another tool to conservationists' arsenal. And that's nothing to brush off.